Hello, Physics 30s. I want to share a little bit about diffraction, interference, and eventually I will do polarization. I think I can just kind of summarize them all together. So, uh, diffraction is basically the third property of light that confirms that it's a wave. And as noted here, diffraction is the bending of light around an obstacle or the spreading out of light as it passes through a narrow opening. Some of those other earlier videos, I think, do a great job of explaining that. This here is a model by a man named Huygens. Um, he had proposed that light wave fronts are really made up of a whole bunch of individual like point sources or wavelets, as he called them. So if you look at this, this diagram here, the all the red dots there kind of signify a point source. And obviously the wave fronts will come as they move from left to right, they're going to hit that obstacle. But because each point of on the wavefront can act like a new or act like a point source for a wave, those wavelets, according to Huygens' theory, it was an explanation of how waves could bend around obstacles, or how in this one it doesn't show it, but if you sent a bunch of waves like this moving from left to right and they encountered a barrier like this, well, obviously only uh, a large portion of the waves would just reflect, but there'd be a portion of the wave that would just continue on through that little narrow opening. And what you observe with waves is that the waves will bend around the opening. So what will happen is you'll get kind of circular wave fronts where that part of the wave, like these little parts here that continued through, are just going to be part of a new wave front where you get circular waves emanating from the point or the opening. So uh, we're going to look at a number of different phenomenon that actually we're just going to look at one primarily, which is um, the double slit experiment. And Thomas Young, the videos were awesome on that. So if an object, or if light was a particle, this is a classic thought experiment. If light was a particle, and yes, we often use monochromatic light, mono meaning one color, or sorry, mono meaning one and chromatic meaning one color. If we shine that light on a screen with two slits, if light acts as a particle, it should just create two slits on the back wall, kind of like a stencil. Or if you're spraying a stencil with spray paint, you would only expect paint to be in the gaps or in the holes. What's really fascinating about light is light doesn't do that. If light's a wave, and I'm borrowing these from Mr. Brent Klintberg, by the way, from studyphysics.ca. He did an excellent job of compressing these. If light's a wave, then as light comes through each one of these slits right here, then behind those slits, the first thing that will happen is diffraction. So you'll get kind of circular wave fronts emanating outwards from those 2 points, and we get what we've seen in physics 20 as a classic two-source interference pattern, where we have, the crests from one source are lining up with the crests from another source. Okay, and you have crests and crests and troughs with troughs producing an interference pattern on the viewing screen. So why we tie these together is because in a double slit, the first phenomenon that happens is diffraction. That happens first. And because of diffraction, um, the waves interfere with each other as you move away from the two slits. And the evidence of the interference is the interference pattern that's seen on the screen. And it's always symmetrical. And we're going to look at the components of that right now. So part of what happens too is the pattern like I already mentioned, it is symmetrical, but it can change depending on how close the slits are and how far away the screen is. You move the screen farther away and the pattern will get farther apart. Bring it close, just the screen closer to the slits, then the pattern will come together. And all of those variables are, I'm going to cover those in 1 second. I should just review though interference, and I've done that here in your notes. When crests line up with crests and troughs with troughs, the amplitudes add together. We call this constructive interference, or waves being in phase. So that's where you have a crest from one meets up with a crest from another, and they superimpose on top of each other. We call those antinodes or bright order fringes. That's some terminology that you'll see when we're talking about what it looks like on the screen. When the reverse happens, when crests line up with troughs, the waves cancel each other out and they cause what's called destructive interference. Sorry to cross that. And that means the waves are out of phase. So this produces what are called nodes. This is an area where the light has effectively canceled itself out, and you'll see darkness there. So here's an attempt to try and explain the interference pattern using wavelengths of light and actually showing it as a wavelength. So if we kind of zoom in right here on this top, you can see that the crests and troughs are starting to line up. Okay, so they come in so that the crests and troughs line up, and at the point that we're identifying here, they are completely in phase, and so they produce a bright fringe or constructive interference. Just the reverse happens just below it, and this pattern just keeps repeating itself. But we can see here that, see the crests and troughs here, there's a trough lining up with a crest in terms of that one. I know it's not the greatest prediction, but there you would have destructive interference. So we call these areas of interference nodes and antinodes. And you might recognize even from the video, this middle one was called the central maximum. Okay, the central maximum, because right there is where you'd get the brightest line. It's typically right between where the slits were. Like if you go right behind the slits, right in the middle of the slits, where there really shouldn't be any light if it was a particle, there is a central maximum. So we identify these areas of brightness with using the letter N. And typically we use the whole numbers. This one's also showing the halves because the whole numbers going above or below the central maximum identify the antinodes. So it's the areas of constructive interference. So actually this diagram on the left reminds you what a standing wave is. If you remember that from Physics 20, this may just jog your memory on why we use nodes and antinodes. Because here it shows a spring that we maybe would have started making a wave like this that came in, and when it hits the barrier, then it reflects and then it goes back on top of itself like this. Okay, so the areas where there's maximum amplitude, which occur right here, and so on, those are the antinodes. And the nodes are the areas where the spring appears to not be moving, just due to the symmetry of the pattern that's created. And if that helps you when you're thinking of the interference pattern that's sprayed on the screen, then by all means think of that, because the antinodes are the areas where there's maximum amplification or constructive interference, and that's where the light is the brightest. So what that really means is this captures all of the variables that you need to know. The math isn't too crazy here, but what's tricky is remembering what everything is, because there's like 5 variables basically here. So the wavelength is referring to the wavelength of light that's coming in and hitting the slits. D is the distance between the slits. I won't rewrite that because you'll see it. It's in the notes down below. So how far apart the slits are. L is the length to the screen. And X is the distance between the antinodes that you are analyzing. Typically, we analyze from the central maximum out, but not always. Like I could easily say, what is, you could determine X from n equals 1 on one side to n equals 2 on the other side. And X is the physical distance in meters. Okay, so X is kind of fluid. We typically do it in this fashion here where you measure from the central maximum out, but not always, so be ready for that. And then hopefully this idea of n is making sense. I know we just got talking about n is the index of refraction. I'm sorry about that. Here in this, n is the number of antinodes. So n equals 0, that's the central maximum. And then you can see n equals 1 and 2 going away from the central maximum. And that just goes almost indefinitely. Like, the next one would be 3 and 4 and so on and so on. And it is a symmetrical pattern. These antinodes would be in a symmetrical pattern. Okay, so this is the review which you'll need to get some practice on. There's just a couple of little clarifying points. So we've already talked about X, D, N, and L. So let's look at a couple of these just quickly. D, the distance between the slits. I'll try and emphasize this in a little bit of practice. Sometimes it doesn't give you the distance between the slits. Sometimes it gives you the number of slits per meter, or sometimes even per millimeter. Like, for example, I've seen, say like 600 lines per millimeter. Okay. And as an example, when diffraction gratings, actually they're called diffraction gratings. These they're basically sheets of plastic that have multiple slits in them, like hundreds or thousands of slits. And what scientists realized really quick after Thomas Young was, hey, instead of just using 2 slits, what if we used a whole bunch of slits? More and more slits should define the pattern better, and that's exactly what happens. But how do we get a whole bunch of slits in a small space? What they realized with some practice is you could take glass or a clear plate of some kind, and then you scratch it. And just like on your windshield, if there's a crack in your windshield, the light doesn't really go through that very well. It kind of gets broken up. The scratches in the plastic or the glass act like barriers. And so the light doesn't go through those, but it will go through the unscratched glass in between the scratches, if that makes sense. So that way, scientists quickly realized they could make what's called a diffraction grating, and that can have a whole bunch of lines per millimeter, as I noted here, 600 lines per millimeter. But what you have to catch, though, is you wouldn't use 600 as the distance between the slits, because there's really 600 scratches in between those slits. So in this case, 600 lines per millimeter, what we would really need to do is get that into lines per meter and then reciprocate that. So we could then get meters per line. Okay. And so just to make that basically work here, so 600 lines per millimeter, what we could do, maybe I'll just move this over here so we can kind of maybe draw this in here just a little bit. So 600 lines per millimeter. What we can do is say, well, there are 1,000 millimeters in 1 meter. Okay, so obviously if there's 600 lines in a millimeter, then how many lines would there be in a whole meter? So obviously we'd go 600 times 1,000, and we get basically 600,000. But now we would need to reciprocate that. Oh, sorry, wait. That would be lines per meter. And then if we reciprocate that, we get meters per line. So 1 divided by that, oops, will give us, sorry, my calculator's acting up here. Okay, so this would be 1.67 to the negative 6, okay? Meters per line. Sorry, I kind of jammed that in there, but 1.6 to the negative 7 meters per line. So that's an incredibly small distance, but obviously we're dealing with wavelengths of light, which are in nanometers, and ideally you will get better diffraction if the distance between the slits is close to the wavelength of the light. And you might have caught that from the other videos before. So, if I just have really big slits here, like 10 centimeters apart, and I shine light through it, well, you may not see diffraction very well because the distance between the slits isn't even close to the wavelength. So that's definitely a tip to remember when you're analyzing D. Okay, so be really careful. You don't just grab a number and assume that it's D. Make sure that it is meters per line, and then the math will work. N, I don't think N is too bad. You typically whole numbers. I did make the note that if you're dealing with nodes, then those would be on the halves. So, and the distance from the central maximum. So N equals 0.5, 1.5, 2.5, and so on. And then L is just the length from the slits to the screen. Okay. Notably, everything's going to come out in meters. Okay. So if you look at the formula here, X times D over NL, you'll basically get meters squared over meters because n is just a number here. So you're going to wind up with meters for your units for the wavelength, which is what we need. Okay, so as long as everything's in meters, it'll work. There is a little catch though with this formula, and I noted that in bold here. It says we can only use this for small angle approximation. So the angle of diffraction, which I didn't really show too much here, so maybe I should come back and just show you this. The angle of diffraction needs to be less than 10 degrees in order to use the wavelength equals xd over nl. We basically measure that angle. We take like from right in the middle, basically, of the slits. And then if I was going to analyze the angle, say to where n is equal to 2, so there'd be light, obviously, that would be traveling in that direction. And we look at this angle right there, theta, as the angle of diffraction. Okay, so it's the angle of diffraction, the angle from basically this straight line from in between the slits to the central maximum in either direction, whatever that angle happens to be. Okay, so if that angle if it gets too big, then what you just need to know is if it gets too big, then using xd over nl won't be accurate. I'm not going to try and show you all the math for that, as long as you just know that tip. There is another formula though, and you may have noticed that there's two on your formula sheet. You also have this formula here. This one actually takes the comparison of x over L. Okay, so actually, if you look at this in this example here, x would be this distance right here. That would be the distance from the central maximum to the antinode we're analyzing, and this distance here would be equal to L. And so if we were looking for this angle here, we would go x. We could find it by using tangent. Tangent of theta would equal x over L. Okay, opposite over adjacent. It turns out for basically for really small angles that tangent of x over L is the same as sine of theta. Okay, and so getting that angle means that all you need to understand is that you can also use this second formula, okay, where basically what we've done is we've taken that x over L and we've replaced that with the sine of theta See, D is still in the top and N is still in the bottom. But this one produces more accurate answers in terms of the analysis. So you just try and use that one whenever you can. You know, if you're given a formula, or sorry, if you're given a question though, and you're given, you know, let's say X and N and L, and you're trying to solve for D and you know the wavelength, well, then just go ahead and use this one, okay? Typically, that's not too complicated in that regard. Most formulas will direct you to either one, but just know as a matter of principle that we should watch that the angle is less than 10 degrees if you're going to use the first one, okay? So this bottom picture is just a reminder of another principle that I should mention because you'll see it on occasion, and that is it's the idea of pathway difference. And the why that's important is let's just define it first. So this one shows source 1, which is right here, and source 2, which is right there. And it says that at the first antinode right here, there's basically 10 wavelengths, okay? So I'm not going to really count those, but on that path, 10 whole wavelengths will fit in that much distance, and then they will arrive at position 1, or at n equals 1. Those wavelengths will arrive in phase with wavelengths coming from the second slit, or S2. And in that case, if you can imagine, there's only 9 wavelengths in that one. Obviously, I didn't sketch exactly 9, but what you need to note is that the pathway difference is effectively, look, you have 9 wavelengths here and 10 wavelengths here. So the pathway difference at position 1 is 1 whole wavelength. Okay. Anytime the pathway difference is a whole wavelength, then you're in phase. Okay. So this means constructive interference. It means you're going to have an area of brightness. It just basically means, sorry, that the wavelengths are going to arrive in phase. What's really easy to note, once you understand it, is if the pathway difference is out by half a wavelength. So if the pathway difference is, 0.5 wavelengths or 1.5 wavelengths or 2.5 wavelengths and so on, then you are no longer having constructive interference, you have destructive interference, okay? So that's what's happening in between the nodes, or in the antinodes, right? So in between the antinodes, the pathway difference would be any function of the wavelength that is 1/2, or any fraction that's a half of a wavelength. So if you see that pattern, that's the example of pathway difference. So I'm going to close this video for now because I will post the answers to these. These are just 4 quick questions that get you to analyze diffraction and interference.